Hello, welcome to our Image Quality Lab. My name is Uwe Hartmann. I'm the CTO of Image Engineering. Together with my colleague Janine, we will show you today how to measure the performance of a camera sensor. And the camera sensor is the most important part of a camera, but the configuration of it also contributes a lot to the performance. With the equipment that we're going to show you today, you have great tools to measure performance and the configuration of your sensor.
A modern sensor in a car features HDR capabilities, so high dynamic range, so that it can cover a huge contrast between lowest possible luminance in the scene and the highest. To achieve that, multiple techniques are used these days. You can see in this graph how an SNR curve looks like for an HDR sensor. So it's the same sensor configured once for 120 dB and then reconfigured for 144 dB dynamic range. So the dynamic range would be from the maximum where it reached saturation to the lowest end where we have an SNR of 1, where we have loss of information. But something that people often miss is that the dynamic range is from the extremes, and what happens in between is not really told by the dynamic range number. So you can have effects like this on the right, where you have counterintuitive that brighter areas show more noise than darker areas. How does this happen? Well, here we have a multi-exposure HDR. So multiple images are merged together to create this image. And depending on the configuration, you will have that in certain intensity regions, the dark region from one image is merged with the bright region from another image. So to extend that. So you get from the noisy part of one, you go into the less noisy of another. So this is also shown here in the SNR curve, but there are other effects where you have a loss of contrast that might have an impact on your imager. So these SNR drops, how does that look like? So you see here that are slides presented at Electronic Imaging and work together at IEEE P2020. And you see in the top right, that's image effects, how it looks like when you have these SNR dips. So you have this gradient in the sky, and in the brighter region you have more noise than the darker. That's not really intuitive, but that is what happens if you have multi-exposure HDR or other HDR techniques where you combine multiple images. Also, when you when you create high dynamic range images, we see that here in the example. So when we have the high dynamic range off, we have saturation in the end of the tunnel. That's of course a problem because now the car cannot see beyond the end of the tunnel and there might be something important, so that should break down. But when we create the HDR, you also see that we have a lower contrast in some regions of the tunnel. So the contrast is something very important, and that really goes along with the HDR. So that's why measurements like dynamic range and SNR is not sufficient these days anymore. So we need more metrics, we need a better description how to exactly describe the effects, also in terms of local contrast or what happens in the image. You see that here on the left, that's an example in real life. How it can look like in the lab is on the right, so that we locally lose contrast and that some of these patches are just not differentiable. We cannot differentiate these anymore. So who's working on that? That is, for example, IEEE P2020. That's a work group formed at IEEE that worked for many years now on releasing a standard how to measure image quality in automotive. Disclaimer, I'm just part of the work group. I do not represent the work group. I do not represent IEEE here, so everything I say about that is my personal opinion. So the P2020 standard will be released at end of 2024, hopefully, and that describes also the methods that we show here. So the P2020 standard has also a section that describes how to measure noise, the SNR. That is useful as this is a very established metric, and still there are some differences how people measure it. But I think what is most interesting are some new metrics that are developed in that work group. So really new are contrast performance indicators. So we have, under this umbrella, we have two different metrics that are similar but not the same. That is the contrast transfer accuracy, CTA, and that is contrast signal to noise, CSNR. You might have heard over the years before something like contrast detection probability. And that is also a measure that was used under that name for many years, and it was developed under that name. But after a while, the work group decided that this might be slightly misleading, the name, so that's why it's recalled and renamed to contrast transfer accuracy. But every work that you have seen before regarding to contrast detection probability, it's the same. CTA was just a subset of that. So the idea is that we want to measure how contrast is preserved or how contrast is transferred through the camera system. So we have a real life scene where we have objects, where we have certain image content, and the camera is supposed to reproduce that. And if you want to say how well can it do that and how can it be used then for machine vision applications, we can say if the contrast is completely lost, there is no information anymore. How exactly a machine vision algorithm can handle it is another topic, but exactly we can see that if there's a loss of contrast, we are sure there is nothing that a detection algorithm can do. So we have our camera, we measure the contrast in real life, and then we want to see how can it handle that. So we can go from the scene to the lab and replace the scene with a test target, where we create different contrasts at many different intensities, and that's what we can give to the camera. So with this measurement in the lab and the results that we get from these, we can make the link to the real life scene and say, okay, this could have been detected, contrast could have been preserved or not. There are different ways how to measure the contrast performance indicators. There's the spatial recording, where we use test targets in the scene, and there's a temporal recording. The temporal recording means that you place the camera in front of a controllable light source and you just switch intensity and capture images. This only works if you have full control of the camera, and only works for really raw data, so that you can freeze exposure time, adjustments, or any kind of image enhancement that are scene dependent. That's not possible to capture with the temporal recording. For that, we need the spatial recording, where we provide many different luminances or patches to the camera under test in a test environment. So we have the spatial recording. That means that we can provide a lot of different patches to the camera. Each patch has a luminance, so that forms different luminances, but also different contrasts. And with that information, we can perform the contrast performance indicators with charts in the scene. So we pick two patches, they form a certain contrast, they have a certain luminance, and with that we can calculate the CTA or the CSNR. The interesting part of contrast performance indicators is that we use maps as the main source or the main output for visualization of the results. So the typical output is that we have a map where you have on the x-axis the scene luminance, so the average between the two patches, and on the y-axis we have the contrast between the patches. So that way we can see the impact of contrast and luminance at the same time. And that is very important with modern sensors, because that also where like an SNR measurement would fail. It cannot really tell you things about contrast, only about the noise. And here we can really see both combinations and can derive useful information for our use cases. So first thing is we capture the images and we measure the OECF, the optoelectronic conversion function. So how does the camera under test convert scene luminance into digital numbers? If we know that, we can then also transfer digital values into luminances and then perform the measurement in the luminance space. So that kind of we linearize the data, we use really the data that is also captured by the device under test. And you can see, so we have what we provide technically to the camera, to the ISP and the entire camera is two inputs. So that is just the lower luminance, so L-min, and the higher luminance, L-max. And that is transferred to the camera, and that gives us two distributions. So due to noise, due to any processing in the ISP or in the imager, that will give two distributions, and that's what we use for further calculation. So if we have the two distributions, we can then calculate the probability density function. So that tells us what is the distribution of contrast between these two distributions. So we randomly pick one pixel from one pixel from the other distribution, and then we do that over and over again. So with that, we get the probability density function of the distribution and can say how much spread do I get, how likely is it that a certain contrast happens between these two patches. If I now can connect also with the known luminance that we have and calculate the Michelson contrast, so then I have the target Michelson contrast and I have the real contrast that was created by the camera in its distribution. So then we can take this probability density function and define borders. So I can say if it's below that or above that, it's not useful for my machine vision application anymore. So I can reject that. So I have my bounds and I can say everything that is inside that contributes to my score and everything that is outside does not. So that means a CTA of 100 is that the whole distribution falls within my boundaries. And the lower it is, the more values, the more contrast that we measured are outside of my boundaries. So that means that the device was not able to reproduce the contrast or used a larger distribution, so added, for example, more noise. So when we have now our map, we see certain regions. So here encoded in yellow, that is a high contrast transfer accuracy in yellow. So that means that is a region where we get best performance of the camera. So for a certain contrast and a certain luminance, that's a region where you want to go. But in the dark blue, where it goes towards zero, that's where we have difficulties. And that is typically low light, so low luminance, and low contrast. So that is really where the challenge is. It depends on the use case of your camera if that is of interest. So if you want to detect traffic signs, you have a higher contrast, so you don't have to go there. But if you want to be able to detect a pedestrian with dark clothes at nighttime, you really have to go into low light, low contrast regions. And that's where you need to enhance your camera and need to configure your camera for. So that's where we can do the linking. So you see here a scene where we have different occasions with different contrast and intensities. So we can see like here on the left where we have the headlights and the car, that's a very high contrast. So that's something that we see in the heat map as well. But we might have here in the lower left as well a dark object on the dark road. So that's low light, low contrast. That's really a challenge. Another thing that happens in cameras, and that is not really measured by traditional metrics, is flicker. So you see here an example from a car approaching a tunnel, and you have this traffic sign that shows the speed limit. And you see it goes on and off, and that's an effect of the LED frequency of the LEDs that makes a traffic light and the capture procedure or the capture time in the camera. And that causes flicker artifacts. So that's also something that we can reproduce in the lab. So we use our Vega light sources for that, where we can have control, where we have full control over the frequency, the duty cycle, the intensity, and the phase. So we can control a lot of things, so to really investigate what triggers a lot of flicker issues with the device under test. So the idea of one metric that we use there that also creates a map is the MMP, the modulated light mitigation probability. So let's assume we have a flickering light source and we capture it with a camera. What typically happens is that we get some form of either the intensity goes on and off, or that some like bars or certain regions move through the scene and get brighter and darker. So if we now observe a single pixel in that image, we will see with flicker, we will see that it goes high value, low value. So it will fluctuate, it will go bright and dark. So from that, we can create also a distribution. And if we track that over many frames, what we will see that we have a bright and a dark region where we get peaks. And we will can see that as an indicator if we have these two peaks, so distributions outside of our normal mean value, that means we have flicker there. So that means we can, if for a device that has a good flicker mitigation or does not show flicker at all, we will have the distribution just around the measured value and everything falls within our boundaries. But as soon as we have the flicker mitigation off, we will have the effect that the distribution are outside of our measure, so they fall outside of our boundaries, and that means that we cannot get that we get a lower score for MMP and an indicator that we have flicker in the image. For that configuration that we had at that point in time, so for the frequency and for the duty cycle and the phase at which we measured. So we also get a map from that, and you see here it's a complex map, but it tells you a lot of things. So we have here the 4 different color channels that we have, and this is a measurement for 10% duty cycle and 10% tolerance interval. And then per map, we have on the x-axis, again, the luminance, so how bright is it? And on the y-axis, the frequency that we actually used for, that we checked. So this map, and then in color encoded is the MMP value. So as we said, yellow 1 means there is no flicker. And if it goes towards blue, there is definitely some flicker. And we can see here nicely in that plot, around 100 Hertz, the flicker mitigation does work, there is no flicker. But as soon as we go above, we have region at certain intensities where we have significant flicker, and then at 200 Hertz is gone again. And this is a typical thing. Flicker mitigation in the sensor does not mitigate all frequencies in every occasion. It mitigates flicker for certain defined frequencies. And that's what we can nicely measure here. Okay, so how can we measure that? For that, we use the VLS, the Versatile Light System. So I hand over to Janine, and she will present the product to you. Thank you.
Hello, I'm happy to introduce you to the VLS, which is the short form for Versatile Light Source. I will start with a short product presentation. Then I will demonstrate the measurement and show you the evaluation with our software. You will see that the VLS is a very flexible and reproducible solution for optimizing sensor configuration. We will now start with some technical data on the Versatile Light Source, short VLS. The VLS will allow you to measure 4 P2020 metrics with one device. The metrics included are MMP, modulation, mitigation probability, CTA, contrast transfer acousticity, dynamic range, and CSNR, contrast signal to noise ratio. The VLS consists of 6 Vegas. These are connected by individual arms. This enables flexible alignment of the light source. This is an important point to prevent influence of flare during measurements. With the VLS, you can challenge your automotive camera and sensor system with typical illumination situation. The entry setup is compact, and the same test can be repeated worldwide. The Vegas are DC-driven and highly stable light source. We can see 1 Vega here. It is also temperature stable within half a degree. Among other things, the waveform and frequency can be set for light modulation. This is important to be able to evaluate the flicker behavior. The Vega is sold with a control box, which you can see here, and the software. The box can operate up to 7 Vegas simultaneously. To create different contrast in a scene, each Vega has the option of mounting grayscale test charts, which you can see here. There is also a color chart, calibration plate, and neutral intensity filters, which you can mount magnetically in front of the Vegas, depending on your requirements. We can also customize charts. There's also the option to have a light hood in front of the Vega to avoid flare during the measurement. We see here now a typical setup for a measurement. In front of the VLS system, the camera is placed. The camera is connected to a computer and we can see the live screen of the camera here. The live screen is really helpful for aligning. For aligning, it's not important that the VLS system is centered or symmetrically in front of the camera. Also, the angle of these light sources is not important. What is important is that the fields are visible completely and that there is no flare. To avoid flare, it's really helpful that these light sources are movable and flexible, and you can shift them so you can avoid the flare. The last point you have to take care for in alignment is that the camera is close enough to the VLS. The setup now makes it possible to bring the real-world challenge into a test environment that can be controlled. Different image quality factors can be tested under certain conditions. In addition to the lighting conditions, the temperature can also be controlled using a climate chamber. In this way, the same scenario can be tested repeatedly worldwide under the same condition. Let us now take a closer look at the VLS control software. This is the VLS control software. In the device status, we can see that all Vegas have been recognized and their runtime. The light control is a helpful function for alignment. You can use this function to change the intensity of an individual Vega. If we now want to measure contrast transfer accuracy or short CTA, we must first generate a sequence. To do this, you can drag the respective element into the sequence line. Afterwards, we can change the option here. We can adjust the duration and the luminance shift. For MMP, it works quite similar. You can drag down the MMP elements instead. And of course, the options are different. We can now run the sequence. After successfully running through the sequence, this plot shows us the luminance as a function of time. And a ref file can be exported. This is necessary for the evaluation. A sequence can also be imported so that the same sequence can be played at another laboratory. The room must be darkened for real recording. An image sequence or video recording must be captured with the camera to be tested while the sequence is being performed. After a few minutes, the measurement is usually completed and we can continue with the analysis. To do this, we start the VLS evaluation software. For evaluation, the first step is to open the ref file which we saved in the VLS control software before. The raw images with the sequence recording are also loaded. We fill out the right frame rate and the raw file attributes. Now we see the loaded images and can change the maximum and minimum digital values. The first step in evaluation is to let the sequence detection run. If it fails, the region of interest can also be adjusted manually. In that case, it was successfully. The next step is to select the KPI ROI detection. We now can select the metric we want to evaluate. In case of contrast transfer accuracy, dynamic range, in CSNR select this tab and then perform these two steps. In case of MMP, you have to select this tab and perform these 2 steps. Of course, you can also change the option and change the CTA threshold, for example. Since the evaluation takes time, I won't show the steps here. After the evaluation, the results are displayed here and here. In addition to the results, in this field you can see the luminance of patches. The result can be linked to the captured images. Direct validation is therefore possible. You will find numerous other metrics under the Contrast Result tab. As you can see, the result of OECF, dynamic range, CNR, CSNR are generated with these of CTA.
Thank you, Janine, for introducing the VLS to us. So now, what do we get from that? So one, beside many other measurements that we get, is the CTA heat map. So you see that here from 2 cameras. These are automotive grade cameras. Let's call them camera A, camera B. And we get these 2 heat maps. So you see that the heat maps are different, but what does it actually tell us? First of all, let's have a look. What does the heat map show us? So here on the x-axis, we have the luminance. So that is how bright is a certain scene. And then we have the object contrast expressed here in Michelson contrast. And then in color, we have the CTA. So what does that mean now? So if we have a CTA of 1, it means we have perfectly reproduced the contrast. So the yellow area here, that is what we would like to have. And now if we go to the left, it turns out that it's going to be reduced. That's because it gets darker and darker. So here on the left, that's what's low light. Here on the right, that's what's happening in saturation and in bright light. And then if we go from top to bottom, we see that it's a loss of contrast. So while, for example, here at 1 candela per meter square, a high contrast object is still well reproduced, if I reduce the contrast, a low contrast object is not reproduced. That's also logical, so we have more noise kicking in, we have other effects. But that is how we can see this map. Okay, now we took the cameras into the lab, but we also took the cameras into real life. So we took these 2 cameras, automotive grade cameras, mount them in the car, and then we took a Solectrix Skive high performance frame grabber and soft ISP. So that's a very powerful tool so that we can have a software-based ISP for these cameras in real time and then record in parallel during different situations. With that setup, we caught a lot of different test scenes, like you do in your projects, like going through a tunnel with a lot of changing light situations, which is a challenge. Or here to catch the pedestrian on the left. Or now on the left, the car approaching us. We will see that in more details in our results, what's going on there. Or here, purple highlights, also something that can be seen with a lot of cameras, an issue caused by saturation from the sensor. Also, for this particular camera, headlights and strong light sources are an issue. So you see the effects here from headlamps or even from the cyclist on the right. And low light, of course, always a problem. Here under the bridge, there's not so much light, but we still need to know where to go. And with today's cameras, flicker is also an issue. You see here, the whole scene is flickering. That's because of the road light, LED-based road light that is causing trouble with the camera. Or any kind of other light sources. So like here, it gets colorful for a moment and so on, a lot of things going on. Okay, so we have these scenes, and how can we link that to the map? So here is an example that we captured. I took a frame here. So the car is approaching a bridge. There is no light under under that bridge. So it gets very, very dark in that region. And because of the headlamps on, and we have huge contrast there towards the scene. So it's now interesting to see, can we actually see something here under the bridge? So road markings, anything to know where to drive. So we see road markings have a certain contrast, but we get into very low light. So if we assume a certain contrast here, but we now move into this region where it gets very, very dark. And you see this camera is dark blue in this region here. So that means it cannot reproduce the contrast, it cannot maintain the contrast. So we really have a loss of information in that region. So to differentiate a camera that does better in low light to another, this is the region where we have a look. Low light, and then also in low contrast or medium contrast. But we see anyway, even if I increase the contrast, I don't get to really good performance, then I'm still here at like 20% CTA. So that's how we can see this map. Or here where it doesn't get that dark because we are in daylight, but we enter a tunnel, and because of exposure control and so on, this is challenging. And we see here, like on the left, so here on the left you see the processed frame, and then here I put a detail out of that, and you can hardly see they are two people. So dark clothes with dark background, that's really challenging. And also in the RAW, it's hardly to get that. Of course, I had to process the RAW here to make it somehow visible. But now we can also have a look in our map here. So we see we have a low contrast, very low contrast object, and it's not extremely dark, but it is low contrast. So we go into this direction and we see, okay, here there is still very low performance or lower performance in this region. So this is where we now know, okay, that a device struggles a bit. When we have a look at another device, so here also in the raw data we get some contrast, and if we go here, it's we have more yellow regions. So the yellow region goes further down, so to say. So that means we have a better performance in detecting low contrasts. And that is, that's something very interesting here to see. So we can say, okay, even low contrast objects are better preserved by this camera, beside of that peak where we might have some loss at a certain intensity, which we don't see here. Okay. Another effect that we see, and that is something that is similar to the peak that you saw before, is that when we go through different transition zones of the camera. So we have an HDR sensor, and typically HDR sensors have trouble at some certain intensities, because that's where maybe they merge multiple exposures or merge other information. And we see that here, if you have a closer look at this silver car, so there is a certain contrast from the windshield and the body of that car. And when the car is still outside, we get it. When the car is fully in the tunnel, we get that. But in that transition, when it just enters the tunnel, we see a lot of loss of contrast here. The headlamps make some trouble. That's also something that we can see here, but also we have this loss in contrast. So what that means is we have a certain contrast that isn't that high, so because of the silverish color in the body and so on, so there's not so much high contrast. And then we can move on horizontally through this map, and we see that there are different regions where the CTA is lower, so it reduces, and that's actually what we can also see here in the image. Also, it's not only all about low light, it's also about bright light. What happens in the highlights? And something that I've seen in many misconfigured settings is here these purple highlights. So you see the sensor down here performs much better in that term, so it reproduces the highlights. While this camera here, I mean, it fails even to reproduce the clouds and gets into these purple issues wherever something is bright, is very bright, like here the reflection of the car and in the sky. That's what we perfectly see here in our map. So you see here that region here, that is where it's very bright, and we have a dark blue there. Dark blue means very low contrast transfer accuracy, so the actual contrast that's there cannot be reproduced, mainly here now due to saturation effects. And that's what we nicely see in our map, that there is an issue with that camera. So this issue here, you don't need to drive out, you can just get that from the map. So getting information in the lab, that's very important. So when you have a project involving a camera, so you have a design phase where you say, okay, how should it look like, what should it do? Then you start the sourcing, what sensor do I use? You develop the camera, then the basic configuration, fine-tuning, and at the end, the validation, does it work as I want to? What I see a lot is that people are working with incomplete and retests in the lab, in the whole chain. So a lot of issues off cameras, off system, just show up in the validation when the whole system goes on the street and when you start driving. But when you see a problem, then you have to go back all the way in the chain and start again. So you have very long development cycles and you get a very risky timeline. And at the end, of course, not an ideal product. So how we see it, and with the tools like a VLS, you have a lot of different metrics that can help you to identify issues very early on. So even when you start sourcing, get 2-3 different sensors, test them, and from these maps you can tell how good do they perform for my task already in the lab. So with complex and state-of-the-art tests in the lab, at each stage you can do tests and already find issues at that stage, so that when you do a validation, the chance that you find something is at least significantly reduced. And even if you find something, you have much shorter cycles, because you know when things have been introduced, what happened in between, so you get a stable timeline and best performance of your product.
So, thanks for watching, and if you have any question, please don't hesitate to get in touch. Thank you.